this new lecture. In this lecture, we're going to look at random numbers. In particular, we're going to look at a Monte Carlo simulation. And we will juxtapose it against dynamical simulation. And that will be covered in the next lecture. But for now, Monte Carlo simulation is a way of generating states. So different states of a system and then finding out the statistics of those states. Whereas a dynamical simulation is something in which you evolve a certain state over time. You don't randomly generate a state, but you let the states evolve. But the point is, in each of these kinds of simulation, you need to sample various random numbers. Okay, so sampling happens from a distribution. So imagine you have a probability distribution function. So I'll tell you what it is. So a PDF which looks something like this. Alright, so the PDF, if we call it f of x, so it must have certain properties, and the most important property is that integral x naught to x max of fx dx must be equal to 1. So the integration, so x is the random variable, f of x is the probability density function of the random variable x, and the integral from x naught to x max must be 1. That is, the total probability of all the variables x must be equal to 1. And this is quite similar to the toss of a coin, where each, or rather the roll of a die, where each phase has 1 by 6 probability and you have 6 phases, so the summation of all probabilities is equal to 1. So this is more of a discrete probability distribution, whereas this is more of a continuous distribution, and the way to quantify it is through a probability distribution function or a probability density function. And so the higher value over here means these variables are more likely to occur than these variables. Okay, wherever the PDF is low, or the value of the PDF is low, you have a lower probability of sampling that number. So uniform distribution is something like this, meaning that all the variables have equal probability of being sampled. Okay, so suppose this goes from 0 to 6, right? So the uniform distribution, can you tell me what form it must have? So integral of f of x from 0 to 6 must be equal to 1, and because f of x is equal to constant, so this is simply constant times 6 equal to 1, so the constant is 1 by 6. So the probability density function in the case of a uniform distribution is simply 1 upon x max minus x min. So I mean, this is in a nutshell. I mean, as we go along in this lecture, we'll see various things and how they can be of various utilities, and we'll see how to approximate pi using the Monte Carlo simulation, a very classic dart throwing problem. And then we'll look at a very um, famous problem. It's called as the Buffon needle problem, in which we also get an approximation to pi. So let's begin. Let me select the Python kernel, and yeah, so straight away let me import all these things from a previous snippet, and these are things we would require regardless of what we're trying to do. It's just bringing in an interactive widget, numpy. We will need scipy later on, but we will import it as and when we need it. All right, so the first thing is, let us find out a bunch of uniformly distributed variables. So let me run this. All right, so let us define the number of samples as n, and let me define it as 10,000. All right, then let me define s as the samples. So s will be np dot random dot uniform. and let us say we want to sample between 0 and 6, and we will say we want n number of picks. Okay, so this will give us, oh, sorry, this has to be size equal to this. All right, so now what we have done is we have sampled 10,000 variables from a uniform distribution with a minimum value 0 and a maximum value 6. So let me just show you the contextual help for this. So uniform, low, high, size. This is what we need. In fact, if I give this 1, I will get only one value. Let me print it out. So this is one random value. If I run this snippet again, I'll get another random value. If I run this again, run this again. So if I keep running it, I'll get a host of random values uniformly sampled. Okay. So I'll keep it like this. Maybe let me show 10 values. So these are 10 values which have been sampled. All right. So let me also show a plot of it. Now let me do plt.plot s. So now what we have is, this is the array index of s on the x-axis. On the y-axis we have the value, and it sort of fills the entire space from 0 to 6. Because we have a lot of sampling going on, it will appear quite filled. If we increase this further, it will, so ideally we should only plot the points rather than joining them by lines. So let me do this, and let me write marker size equal to 1. Okay, so these are all the various samples. So at a certain x value you have only one sample. Okay, don't be confused, don't think that you have multiple samples for a given x value. All right, and this might be clearer if we reduce this to 50. Okay, so for each x you have one sample, and this is how you sample a lot of numbers between 0 and 6 uniformly. Now what does the np.random offer us? Let us see. In the contextual help, in the module we have this random, which gives us random floats over 0 to 1. We have permutations, shuffling, okay, choice from a random array. So not a random array. If we have an array and we call the function choice, it will select any element from that array. Then we have random. Okay, so these are removed in the new API, but they will work nevertheless. Then we have some univariate distributions, the beta distribution, binomial distribution, chi-square distribution, exponential distribution, Fisher distribution, gamma distribution, hypergeometric distribution. So these are all various types of probability density functions. Okay, we have the normal distribution, which is the Gaussian, you may be aware. We have the Pareto distribution, uniform distribution, which we have just called. We have the Weibull distribution, zip distribution. Then we have multivariate distribution. So when we go from one variable to multiple variables, you have, instead of a single function, you have a surface. All right, so then you have some other standard distributions and all these things. So with the help of this, we can sort of sample various distributions, sample variables from various distributions. Okay, and each distribution has its own set of parameters that you need to give. For example, in the normal distribution or the Gaussian distribution, we need to supply the width of the Gaussian and the offset of the Gaussian. So obviously when we call this, so let me go over here. So now let me go to the contextual help of this. So the location and the scale. All right, so let me set the location to be 0 and the scale to be 1. Right, so now we will have a bunch of values which are picked from something close to -2 to something close to 2, because the Gaussian distribution, when it is centered around the origin, it looks something like this. Okay, it's more likely to sample from the center, that is the neighborhood of 0. All right. So in fact, what is a very convenient way of sort of sampling a lot of points and then telling someone that, okay, look, the sampled points are indeed in this kind of a distribution. So the way to do it is to do a histogram. So a histogram is sort of telling you the number of counts that you have in a certain bin. So we can split this into various bins. All right. And then let me print S. All right. And then what we will do, suppose this is -2, minus 1.7, minus 1.5, and so on. So this is 0.36. So if this is 0.3 and 0.4, in this bin we will increment the count to 1. Now what do we have? Minus 0.38. So we have to increase the bin, so there will be one count over here. Then minus 0.46, and then we will increment a count somewhere over here. So we will look at all the points and we will break up the domain into a lot of bins. We will count the number of occurrences in each bin and we will plot the histogram. It is something which you might have learned in high school. Okay, so because we are sampling from a distribution, we expect more points or a larger count for numbers near the origin, and we expect fewer counts for number away from the origin. So let us see, let us look at how we can do the histogram. So there are multiple ways of doing the histogram. In fact, there are two easy ways of doing it. So one is directly using the matplotlib function. So we have the count comma h comma patch. So but we don't want to access the patch. This will be equal to plt.hist. Then we will pass s. Then we will pass the number of bins. So suppose I want it over 10 bins. All right. So let me run this and show you what happens. So it has created a bin. It has created 10 number of bins. So we have asked the function to give us the histogram over 10 number of bins. So if you count this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has split the domain into 10 bins. All right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it has split it into 10 bins. And what is the edge of the bin? So this will be the minimum value. So what we have is a bunch of samples, S0, S1, all the way to Sn. So it will find out the minimum value amongst these, fix this as the leftmost edge. It will find the maximum value out of all this, and it will set that as the rightmost edge. Then it will split that domain into 10 bins. Okay, it's like taking a linspace, and then it will loop over all the values as 0, s1, and it will see inside which bin it lies. So over here we see that the bin between minus zero point 0.5 and minus 0.15 or something, it has 6 counts. Something between zero point 0.3 or zero point 0.2 and zero point 0.5, it has 7 counts. Something between 1.2 and 1.5, it has 7 counts. But now let us increase the number of samples that we take. Let me make it 1000, and let us run this. Let us see what happens. In fact, let me suppress printing because it's going to print 1000 values. All right, so when we take 1000 values and we still have 10 bins, it appears to give that distribution that we desire. We have more, so we have almost 250 counts near the origin. So we have total 500 counts near the origin, 500 out of 1000. So we have almost half of all the samples lying near the origin, and the other half lies away from the origin. Let me increase the number of bins. Let me increase the number of bins so you get a smoother distribution. Let me increase the number of points. So now we do see that we have this distribution of counts, but this is the distribution of counts. It is not the probability density function. How do we plot the probability density function? We don't want the counts, but the PDF in this case. So essentially we are sort of representing the continuous function as a discrete function, and if we divide everything by the total number, so for example these had 500 counts in total, but we divide it by the number of samples, right? So we will get the fraction of total samples that we have. And once you do that, once you sort of see what is going on, so the total number of all counts will be equal to the number of samples you took. Okay, once you divide it by the total number, you will get something which is going to be normalized. So you go over here and you say density equal to true. Essentially you're dividing by the total number of samples, that is n. So now you get this distribution. All right, so this particular distribution is the Gaussian, but now I have asked it to do the histogram over 100 bins. Alternately, I could have supplied my own bins. So how do I sort of supply my own bins? So I've already said that the bins must sort of go from the minimum value of the sample to the maximum value of the sample. So let me do that. So I will do np dot linspace np dot min of s to np dot max of s, and let's take 50 bins. So now we have a histogram which takes 50 bins. Let me do 100. So we then have this. In fact, if I run this again and again, I'll get a different histogram, because each time I run this cell, I am sort of calling this function again and again, and I'm getting a new distribution. All right. So let us also plot on top of it the analytical expression for the probability density function. So let me remove this and call this bins. Let me declare, sorry, bins equal to np dot, let me copy the code. And let me also plot on top of the on top of this plt dot plot bins comma 1 by square root of 2 sigma square. So this will, because sigma is 1, so this will be simply 2 to the power 0.5 times exponential minus of x minus 0 squared by 2. So the x is not defined, this has to be bins. All right, oops, so it seems I've obtained the magnitude incorrectly. I think there is a pi somewhere. Okay, so it's 1 by square root of 2 pi times exponential of minus x square by 2, and that gives us the appropriate function. In fact, let me write s sig square, and let me write, okay, and let me define this as x naught. So now we will give x naught and sig and we will define x naught comma sig equal to 0 comma 1. I think we have, yeah. So now let me change the offset. Let me make it 1. So now the Gaussian is centered around 1. So you can have a look at the equation. It's rather simple. I'll write it down and you can have a look in the uploaded file. But this defines the offset of the Gaussian, and this defines the width of the Gaussian. So if I make it 2, so then I have a larger spread of the Gaussian. If I make it smaller, I will have a lower spread of the Gaussian. Okay, it becomes much thinner. And in order to really see whether it is becoming thinner or not, I'll limit the x-axis. So plt.xlim, let it go from -5 to 5. So now it appears as a very thin Gaussian centered around 1. Let me make this 0 so that it's centered around the origin. So it was centered around, yeah, it was centered around 1. Let me now increase this to 2. So now it has increased. The x limits are still the same. Let me make it 1, and it's something like this. In fact, what we can do is we can plot a bunch of um, histograms like this for by looping over this, and I'll leave this as a small exercise to you. Just make a small loop in which you are changing sigma and seeing how the Gaussian changes. Notably, once you make it fatter, the maximum value will also change. Can you guess why? Think about it. And once you make it narrower, the maximum value will increase. It becomes 4. So think about that. It's not that difficult to deduce. It has something to do with the fact that the integral of the PDF has to be 1, that the area under the curve has to be 1, right? So now if I go back to the uniform distribution, let me copy this and let me make this as x min and make this x max. Let it go from 0 to 6. I'll change this to x min, x max, and we don't really want to plot this, but instead of this we will simply plot 1 upon x max minus x min, and the limit will be x min minus 0.1 to x max plus 0.1, and I'm offsetting the limits of the plot because I want to show the bin edges as well. So let me run this. It seems we have a small error. Mm, this has to be np.once np.shape bins. So we cannot plot a vector against a scalar. So what I had written initially was 1 by x max minus x min, but it has to be multiplied by a number of ones so that you can have two vectors which you can plot. Okay? So this is a very classic mistake, but nothing to be worried about. All right, great. So this is now the uniformly distributed variables. Obviously there will be some variables which are more sampled, but more or less you have a uniform distribution. If I increase or if I can reduce the number of bins, it should become more uniform. If I take only 10 bins, then it becomes more and more uniform. So think about it, why reducing the number of bins makes it more uniform. So these are certain questions which once you start playing around, you'll get an idea about it. All right, so let us proceed further. Let us quickly take a look at the Pareto distribution because I want to establish a very useful concept by that. So the Pareto distribution is one class of fat-tailed distribution where the distribution looks something like this, right? So in this distribution you must supply the scale of this distribution, that is m, and the power law that it follows, that is A. So the distribution, so if the random variable is x, and the distribution f of x, so f of x will be a m to the power, let me just, yeah, a divided by x raised to a plus 1. So this is the Pareto distribution over m to infinity. So the random variable can lie between m and infinity. This can be an open set. All right. So now let us sample from the Pareto distribution and let us draw the histogram. It's quite simple, but regardless, later on we'll see manually how to do it. So okay, so this will simply become the Pareto, and let us quickly look at the contextual help for the Pareto distribution. Uh, so it's simply taking A and the size. So, mm, so because it's only taking the power law index, what we can do is we can do this, and by default it generates the distribution from 1. Okay, so the mu, what this peak over here is is equal to 1. And in fact, the generalized Pareto distribution is available inside SciPy, but let us use the NumPy distribution for now. So what we'll simply do is, because we are generating something with 1, no, in fact, okay. So the classical Pareto distribution can be obtained by adding 1 and multiplying with the scale factor. So we will do 1 plus Pareto and multiply it with our factor m. All right, fair enough. So 1 plus this multiplying m. So this will give the appropriate Pareto distribution, and the only index that we need is going to be a. So a comma m is going to be, say, 0 or 2 comma 1. All right. So let me run this and see. Have we missed a bracket somewhere? We missed a comma. All right. So there is no, okay. Mm, we don't need the uniform distributions as well. And let us remove the bins, and let me take 20 bins. Let me take 100 bins. Alright, so there is a very high probability of something near 1 and then quickly decays to something like this. And it has non-zero probability for large values. And this is what we see over here. The probability is decaying, but even for large values, it's small, but it's finite. It's not going to 0. That is why you have this. Let us limit the x-axis scale to go from 0 to 10 maybe, and let us take 1,000 pins. Okay, so it looks something like this. So now let us plot the distribution on top of it. So what do we have? Something between 0 and 10. So let me define x as np.linspace 0 to 10. Then the PDF f will be a times m raised to a divided by x to the power a plus 1. All right, so this has to be from 1. Actually it has to be from m. So let me run this, and in fact we have to plot this as well. So plt dot plot x comma f. Let me make it a broken black line. Great. So the analytical expression that we have written over here this particular expression, and a large number of samples that we plucked from the Pareto distribution of NumPy, they are in good agreement, and it should not come as a surprise because in we are sampling from the distribution and then eventually plotting it, so it should not come as a great surprise to you. But I'm just showing you some of the nitty-gritties of how that a m all these things are decided. So each distribution has its own sort of set of parameters that you need to pass along, and depending on the work you have to supply the appropriate parameter. In this case it was a and m, and the default function that numpy gives it is choosing m as to be 0. We only give a, but we can always do this little trick, and the help itself tells you to do that. Okay, so but you can use the generalized Pareto distribution from scipy if you don't want to do this little thing. All right, so now I'm going to show you how to sample from a random distribution or some probability distribution function. So the basic idea is as follows. So if you have a PDF, so if this is X, suppose this is the PDF. So this is the PDF. So what we will do is we will plot the CDF. So this is called as the CDF. So if this is X min and this is X max, so the CDF, so C of X is defined as integral X min to X P of X prime dx prime. So if this is the value X, so the CDF, this particular value, will be the integration of the PDF from the minimum value to that particular value, and this is assigned to this value. So at this particular point it will be this particular integration, it will be assigned to this. So obviously when x becomes equal to x max, so cumulative the value of the cumulative distribution function or the cumulative density function at x max will be equal to 1, because it is essentially going to be integral of x min to x max p of x prime dx prime, and by definition of being a probability density function, this integral is going to be 1. All right, so let us take this distribution and try to work with it. Okay, so I'm going to take this, and in fact let me wrap this inside a function. So my PDF, and let it return this, and the inputs to my PDF will be a, m, and x. All right, so now let x be, and p dot linspace, it will go from m to set 6. We just want a truncated set of variables. All right, so then uh, f or rather the PDF p will be my PDF. This has to be only this. So there's a certain risk you run when you're trying to reuse code, but anyway, one has to be careful. AMX. All right, so let us define a comma m equal to say 2 comma 1. All right, so now let us plot this. So plt dot plot x comma p. All right, so this is the distribution that we have. All right, so now it's only bounded to 1 to 6, but is it really going to be the PDF? And the answer is no, because let us quickly print out the integral of this supposed PDF from x min to x max. So int val is equal to, so for this, for performing the integration, we have to import scipy dot integrate as si. All right, so si dot traps then this will be p comma x. So then we will print int val. All right, so int val comes out to be 0.977. So obviously the value of the integral is not 1, so we must what we call as normalize the PDF. So we must divide it by the integral. So si dot traps, or we can do the following, then p equal to p divided by si dot traps p comma x. So now when we do this, we have the value of the integral to be exactly 1. So now this function which spans over m to 6, where m is equal to 1 in this case, that has a value equal to 1. That integral is equal to 1. So it's a valid probability density function. If it does not have the integral equal to 1, it is not a valid probability density function. Alright, so we can get rid of this. Now let us plot the cumulative distribution function. So C will be equal to si dot come traps, and over here will be p comma x. Then we will do a plot, plt dot plot x comma c. Alright, let's see what we get. We have an error. So okay, once we do a come traps, it ignores the initial point. So we will write initial equal to 0, right? So it ignores that initial point because the initial point is quite trivial. So c of x is this. So if I write c of x min, it will be simply integral x min to x min of p of x prime dx prime, and obviously this is 0 because the line itself has the integration range itself is 0. So we have to declare that, okay, once you do that, you put an initial value of 0, and this is something which you need to do. In Octave I don't think you need to do this, right? So we have this, and in fact let me also draw the line of 1. So then we will do plt dot axv line, or rather h line 1, right? And let me make it as a broken, or let me write color equal to k, right? So that is that limit of 1. So now our task is, I mean, I have used a known PDF, but suppose that function were to be not known and I want to sample a lot of values from that function. So we have over here let me go back to that figure. All right, so let me erase all this. So we have the PDF and we have the CDF. So now how do I sample points from this? That is the question. So the way to do it is, you know that the CDF will go all the way from 0 to 1. So now your task is to find out a random number uniformly distributed between 0 and 1. So essentially, suppose this is that random number, or this is that random number. So now we drop this value on the CDF. Now we see what is the corresponding x you have to that value. Essentially what we are saying is s is equal to integral x min to x p of x prime dx prime. So for what x do I obtain that value of the sampling, or that random value, that uniformly drawn random value? Okay, so let us do that. Let me draw one uniformly let me draw a uniformly sampled random number between 0 and 1. So let s be np dot random dot uniform between 0 and 1, and let me draw only one value. In fact, let me declare it as n, where n will be equal to 1 for now. Alright, So psi is equal to n comma, right? So n comma means it's just a 1D array. So let me print out that value. So s is now 0.164189. Okay, so we have something like 0.16 over here. So now it maps on to this particular value in the CDF. I must find out as to for what value of x does that CDF occur. So how do I do that? So now I have what, a bunch of values of x, and corresponding to that I have a bunch of values of the CDF. So x min, the value of c will be 0, x max, the value of c will be 1. I must make an interpolation between the sampled value so that given the location of the sampled value, I can interpolate over x and find out for which value of x I will obtain that CDF. Okay, so I must first create an interpolation function. So for that, I must import scip.interpolate as SIO. Then I will make C interpolate equal to SIO.interp1D, and I will make an interpolation function of C as a function of X. Alright. So far so good. Now I will, so what is CI? CI is now some kind of interpolant. I must pass the value of S to the interpolant. Alright. So I will say X interpolant equal to Ci of S. Let me print what Xi is going to be as well. So Xi appears to be this. Actually, each time I run the cell, it's gonna generate a new random number. But let's do this. Let's plot plt dot plot. I will plot Xi comma S, and I will put a black marker. So what does it mean? It will show us this corresponding point. So if this is the random sample S, it will tell me for which, sorry, this is not, this is the CDF. So if I have this as the random value S, it will show this as the point which corresponds to X interpolate comma S, right? So for that random number between 0 and 1 which has been uniformly sampled, this is the corresponding X. So let us see. Great. So it lies on the CDF as expected. So we can run this program a bunch of times and we'll obtain different random numbers. Alright. And now let me sample more numbers. So let me sample 10. So when I do this, I get 10 values on top of that. So the values of xi that I get through this inversion process, alright, the values of xi that I obtain are the samples from that PDF that we wish. That PDF need not be a Pareto distribution. We can have anything we like, but that these are now the xi's that we have sampled. And how do I know that the xi's that I have sampled fall under that distribution? We have not shown the mathematical proof. This is not a course where I'm going to show you the proof as to this method, how it helps us to sample values from the required PDF. Okay, what we expect now is if I draw the histogram or the density histogram of xi over this range, I should obtain this PDF that I have. Let us see whether that is true or not. So let me now suppress the value of S and xi, because, so let me just keep the plot. So now I must draw the histogram of xi. So counts comma bins comma patches equal to plt.hist. I must pass xi. Let me take bins as 30, density equal to true. Let me see. um, okay, is it an issue of this? Yeah, it was an issue of this. So I must declare it as 1. This small is just saying that it has n rows and only one column. Okay, so let me take 100, or let's say 1000. Great, we do approach that distribution. Okay, if I increase the number further, the more number of points I take, I get a better fit to the distribution. Let me increase the number of bins to 100. Excellent. So through this technique, we are able to sort of interpolate a uniformly sampled variable with the help of the CDF to find out a random variable from the PDF that we desire. We cannot just give a PDF and we cannot sample directly from that PDF. We must go through this approach in order to sample from the desired PDF. Okay, think about this, go through the mathematics if you're interested. But in general, if you're not so bothered about creating your own probability density functions, you can use the host of the distributions that are available in NumPy or SciPy and get your job done. You don't need to do all this. Alright, so in the next class, we will continue this lecture forward and find out how we can sort of estimate pi with the help of um, a Monte Carlo simulation from the dart throwing problem to the Buffon needle problem. With this, I am ending this particular lecture and I'll see you again next time. Bye.